Picture this. It's 12 a.m. Amazon's biggest sale is live. Thousands, no millions of customers click buy now for the exact same iPhone. Yet somehow the website stays online. Orders go through, payments succeed. But behind the scenes, there is an absolute chaos. Billions of requests are arriving every second. So, how does Amazon prevent its server from crashing? Meet one of the important concepts in system design, the load balancer. In this video, we are going to follow one customer request from the moment they click buy now until the order is placed. And along the way, you will understand how almost everything load balancer talks about. So let's begin. Our customer Rahul clicks buy now. His request first reaches the load balancer. Notice something? It does not go directly to the application server. The load balancer acts like the receptionist of the huge office. Nobody enters the building without first talking to the receptionist. Its first job is simple. Choose which server should handle Rahul's request. Suppose there are four servers. Instead of sending every customer to server 1, it distributes traffic across the four servers. Now, all four servers share the workload. No single server gets overloaded. So, here's the interesting part. What if one of these servers crashes right now? Let's say my server 3 gets crashed. Does Rahul see an error? No, because the load balancer has already detected that server 3 is unhealthy. It continuously checks every server in the background. The moment a server stops responding, it's removed from the rotation. New users are automatically sent only to the healthy servers, and once the server recovers, it's quietly added back. Rahul never even noticed that anything happened. But how exactly does the load balancer know that the server is healthy? We will answer that in few minutes. First, Rahul's request has another obstacle, which is Rahul is shopping over HTTPS, which is an encrypted data. That means his request is encrypted. Decrypting these millions of encrypted requests every second is very expensive. Instead of asking every application server to perform the decryption, the load balancer does it once. It then forwards the decrypted request to the backend servers. Now, the application servers can focus entirely on what they do the best, processing orders. There's the another advantage. So when the SSL certificate expires, engineers update it only on the load balancer instead of hundreds of servers running in the background. Now, suddenly, the sale becomes even more popular. Traffic doubles, then triples. Soon millions of new customers arrive. Without a load balancer, everyone would collapse. Instead, new application servers are automatically launched. The load balancer immediately starts sending requests to these new servers. Customers never notice that the infrastructure has grown behind the scenes. This is what we also call the horizontal scaling. But here is the other problem. Server 2 crashes while processing the request. Normally, thousands of customers would suddenly receive errors, right? Instead, the load balancer instantly redirects all the new traffic to the remaining healthy servers. So most customers continue shopping as if nothing really happened. And this is the one of the biggest reasons websites achieve 99.99% of uptime. Now, Rahul's add an iPhone to his cart. Okay, now the cart is stored in server 1's memory. Few seconds later, he clicks proceeds to payment. Now what if the load balancer suddenly sends him to server 4? Server 4 has no idea what Rahul added to his cart. His cart appears empty. Not a great shopping experience, right? So to prevent this, this load balancer remembers which server Rahul is using and keeps sending the request to the same server. This is what we call sticky sessions. Modern applications often store sessions in Redis instead, but sticky sessions are still common in many stateless systems. So, is everybody load balancer the same? Not really. Now let's see how Rahul's request is actually routed. Now there are two major types of load balancers, layer 4 and layer 7. Let's talk about the layer 4 load balancer. Suppose Rahul is entering a large apartment complex. The security guard checks only one thing. Which apartment number should Rahul visit? The guard does not ask why he is visiting, he simply directs him to the correct building. Now that's exactly how a layer 4 load balancer works. It only looks at IP address and port number. It does not inspect the actual request because it ignores the contents and it is extremely fast. So examples like AWS Network Load Balancer and HA Proxy works on layer 4. Now there's another which is called layer 7 load balancer. Now replace the security guard with the receptionist. The receptionist actually asks what brings you here today. Depending on the answer, Rahul is sent to different departments, right? This is exactly how layer 7 works. Instead of only checking just the IP address and the port number, it actually reads the entire HTTP request. Now suppose Rahul requests API orders. The request goes to order service. If it asks API users, it goes to user service. This is called path-based routing. It is There's also another one which is based on domains, which is like for example, orders.example.com can go to one service while the other can go to another service, and this is called host-based routing. And that's why layer 7 load balancers are heavily used in API gateways and microservices. Remember those health checks? Earlier we saw the load balancer detect failed servers, right? So here is how. A TCP health check simply asks, is the server port open? Fast but basic. And HTTPS health check actually sends HTTP request and expects a 200 OK response. Now we know that application itself is running. There is a third type which we call deep health check. It checks whether the server can reach Redis, the database, external APIs. This helps detect problems before users are affected. Now, depending on the scale of your application, companies choose different kinds of load balancer. We have hardware load balancer like Citrix ADC, which is physical and very powerful. Then we have software load balancers like Nginx, Envoy, HA Proxy. We also have cloud managed load balancers like AWS, Azure, Google Cloud provides. And finally, we also have DNS-based load balancing using Cloudflare or Amazon Route S3. Finally, how does Amazon actually use them? Let's finish the Rahul's journey. His request first reaches a global layer 7 load balancer. If Rahul requests an API, the request goes to API load balancer. That load balancer distributes the traffic across many API servers responsible for orders, payments, or inventory. And if the Rahul requests some static data, the request is sent to completely different server or load balancer, which is why it reaches another load balancer responsible for CDN layers. Now those CDN servers immediately returns images, JavaScript, CSS without touching the backend servers. Because static content never reaches the application servers, right? The backend remains free to process the real business request. That's how companies serve millions of users while keeping website extremely fast. So today we followed a simple customer request from moment they click buy now until the order was processed. Along the way, we learned how load balancers distribute traffic, detect failures, perform SSL termination, perform horizontal scaling, maintain sticky sessions, and intelligently requests using layer 4 and layer 7. Now that you understand what a load balancer does, right? So in the next video, we will dive into how it decides which server gets the next request, covering algorithms like round robin, least connections, IP hash, and some other algos as well. So see you there. If you like the video, subscribe and hit the bell icon.